we are in the second part of the course, and we'll be discussing about RCNN. RCNN is primarily used for object detection, but there is a variant of RCNN called mask RCNN, which is also used for segmentation. So just to remind everyone, one of the primary purposes of this course is to teach you techniques which can do segmentation, where you are actually detecting the boundary of an object, the contours of that, or an easier version of this, which is detection. So you draw a bounding box around the object. In the last couple of lectures, we saw how to implement this using YOLO, but we never went into the details of how the models themselves work. We were always just looking at the final result and just the in-code implementation. But today we'll be going into the details of how exactly were these models developed. What exactly is the theory behind the working of these object detection or image segmentation models, starting with RCNN. So the R in RCNN stands for regions. And I will tell you exactly why there is a regions term associated with the CNN. CNN for simple convolutional neural network. So let's take a step back. Let's say we were in 2012 or 2013, maybe 10, 12 years back. If we were to develop an image, an object detection algorithm, what might we do, right? Because AlexNet was already introduced in 2012. So by 2012, image classification was something that we could have done very easily. But right now we are talking about 2013 or 2014. So you know how to do image classification really well using AlexNet or VGG, other models. But now the objective is you have to detect the group of pixels inside which you have an object of interest. So let's say you have an image like this, which has a car, and your goal is to detect the bounding box around a car with some sort of probability percentage. Then the goal is to get something like this. You need a bounding box, and you need some sort of like a confidence score. What would you do if you were building something like this without any additional thought? What is the most rudimentary algorithm that you might try? If you have any idea, just let me know in the chat. So the question is, if you were building a rudimentary algorithm for detecting the bounding boxes inside which you may identify a particular object, it could be car, it could be cat or dog, what is that you would have done? So while you type the idea, I will also just say it, but feel free to think on your own of what you could have done. So the simplest thing could be something like this. You take a random rectangle, right, which encloses some type of objects inside it. Sometimes it will be background, sometimes the part of the object will be there. And then let's say you are trying to perform a two-class classification where one of the class is a car, another class is truck. So you say you are now going to classify this particular rectangle into 2 plus 1 equal to 3 classes. One class corresponds to car, one class corresponds to truck, another class corresponds to background. So if you have C classes, you try to classify this randomly generated subset of pixels inside this rectangle into one of the three classes. Now, if you have AlexNet, you can easily classify this, right? Obviously, AlexNet will say this is neither car nor truck. AlexNet will easily classify this as a background. So done. You searched randomly in one rectangle, and you found with pretty good certainty that this is neither truck nor car. It's a background. But just think about how many such rectangles are possible. Let's say the actual width of the image is W and actual height of the image is H. And let's say the width of your small rectangle is small w, and the width of your height of your small rectangle is small h. Then basically, you could place the rectangle here. There are many places where this rectangle could be, right? You could have the same rectangle placed here. I mean, let me move it up. It could be here, it could be here, it could be here, it could be anywhere without changing the width and height itself. So it actually will have W, capital W minus small w plus 1. these many regions, these many pixels along the width where you can place this rectangle. Similarly, you will have capital H minus small h plus 1. These many pixels along the height where you can place the rectangle. And since the placement along x-axis and placement along y-axis are independent of each other, you can simply multiply these two. So you have these many ways in which you could place this rectangle anywhere on this image. But that is not it. The width and height of the rectangle itself are numerous. So the width can be anywhere between 1 pixel to W pixels. The height can be anywhere between 1 pixels to H pixels, because the maximum height of the image is H, width of the image is W. Now, if you look at the total number of rectangles like this that are possible, it's huge. So I have made a calculation here. Assume that your width of the image is 224 pixels, height is 224 pixels. You are now looking at almost 635 million boxes, 635 million rectangles in which your object could be there. So basically, now you will be performing a binary, or in fact, 3-class classification of these 635 million boxes. So what are the 3 classes? Truck, car, or background. It's so inefficient because it doesn't make any sense to search all the 635 million boxes. So what is the next best thing to do? You only search at some boxes, you only consider some boxes in which you think there might be this object, right? So those are called as proposal regions. So somehow magically, let's say I told you that, so in this, where is the car image? In this car image, let's say I told you that don't look at all the rectangles. Your object is likely found inside this rectangle, or this rectangle, or this rectangle, or this like this. I propose you a finite number of rectangles, like 2000 rectangles instead of 600 million rectangles. And I tell you that these proposed regions have higher likelihood of finding the object. So all you need to do is check only inside these 2000 rectangles. Now your computation becomes much, much more reasonable. And this is exactly what RCNN does. R for region. So you are, instead of looking at the entire image, you are just looking at some proposed regions inside the image for the presence or absence of the object of interest. So now let's see how this is done. So now you understand, hopefully, what is the difference between the rudimentary approach of searching all the possibilities versus searching some possibilities. So first, what you do is you have an image, right? So the image may not be square shaped, but most of the neural networks, CNNs, that we are going to be using in the RCNN architecture will require square shaped input. So this RGB image will be converted into square shape. So if this was 224 by 440, it will be cropped or reshaped into 224 by 224. Plus, I mean, you'll be multiplying it by 3 because there is red channel, green channel, and blue channel. So as you all know, the images are represented by pixel values. The red channel will have 224 by 224 values, where each pixel value can range from 0 to 255. Like that, there will be green channel, blue channel. Then what do? Then you perform something where you somehow magically get the proposed rectangle regions, which are those 2000 rectangles. Now, how do you get that? So for that, there are certain algorithms which are built using handcrafted logic. So there is no deep learning involved in identifying these 2000 potential candidates. What you look at is, you could look at clusters of pixels with similar pixel value. So here, all these pixels have similar pixel value, like something like a brown or gray or whatever. All these pixels might have some green values. So just by looking at clusters of pixels that may have similar color, you could identify, or you could propose some regions, right? There are also other ways in which using the pixel values, you could define the geometry of an object. So in one of the works that I had done earlier, where two rice grains were touching. So let's say I have two rice grains whose boundaries I can easily find out when they are touching. But to identify whether there were two rice grains or three rice grains or five rice grains that were touching, what we did was we identified a centroid of this shape, something like this. And then we defined the radius of curvature like this. So, I mean, radius, which is radial distance from the centroid to its periphery. Now, if you plot this radial distance function, you can notice that at some point, the radial distance function will reach a minima. So let's say I'm going from theta equal to 0. So let's say this is theta equal to 0. This is theta equal to 10 degree, 30 degree, 60 degree, 90 degree, and like that back to 360 degree. So now if I plot theta on x-axis versus the radial function as on y-axis, you will see that there is a sudden decrease here and then there is an increase. So once theta reaches a particular value, my R will reach something like this and it will again start increasing. So this is one way in which I can identify that there are these regions where overlapping is happening. And if there are two such regions, two rice grains are touching. If there are more regions, more rice grains are touching. Now I'm giving you an example of a handcrafted logic. There is no deep learning. Very similar to that, you can construct just pure engineering logic to decide when you may have clusters of pixels that belong to same object. Now, using that algorithm, you can easily get these proposed regions. You might remember that logic, similar logic we applied in the burglar detection project, where for detecting the burglar, we did not implement any deep learning. We simply implemented a plain logic that included changes happening to pixel values from one frame to another frame. So when we clustered those pixels, you will get a group of pixels, and then you can draw a bounding rectangle around those pixels. And what we did in the burglar detection code was we said, okay, if the size of this rectangle, I mean, if the area of these clusters of pixels are less than 200, discard them. If it is greater than 200, accept them. Now what we do is, now you have many proposed regions, right? Now I have to look at each of these proposed regions separately to see whether there is a car inside or not. So that is the logic that I'm going to describe here, but I will have a couple of questions here. Yeah, so Ahmed, exactly. So the name of this is called selective search. The name of the algorithm, what I'm saying is selective search. So you have an image, right? And this is the selective search proposed, one of the proposed regions, let's say. So this is not the full image. This is, you can say, part of the image. So maybe you won't have access to the full car. You can even say you have only access to part of the car, something like this, maybe. Now this image, which is one of the 2000 proposed regions, you have to classify. So how will you classify? You pass this through a pre-trained neural network such that this 224 by 224 by 3 representation is passing through some convolution layer, and finally it flattens out to some 4096 dimension representation. So this part of the neural network would be like trying to convert this RGB representation into another representation. Now, this representation can be used for two things. One is to perform a classification to say, hey, this subset of pixels, which is one of the 2000 regions, has car, has truck, or has background. So it will perform. So this classification will perform a 3-class classification. And there is one more thing which performs a bounding box drawing. So there are two actions that are happening. I will repeat all of this once again. So first you have an image of a car. Then you will create 2000 proposals using selective search. Now you will have to process all the 2000 subdomains instead of 600 million domains, instead of 600 million boxes. You will process each of this separately. But now I'm going to say one example. So let's say you pick 555th proposal. Proposal means 555th bounding box. Then you convert the bounding box into a square image. you resize it into a square image, you pass it through bunch of convolution CNN operations. And what happens is this 224 by 224 by 3 image will become something like 4096 by 1 representation. Now this representation, which results from a flattened layer, from this you have to do two things. One is, first you have to say whether there is a car or truck or background. This you have to say. Is that enough? No. You also have to say if car or truck is present, where exactly it is. So you have to draw a bounding box. So you also draw a bounding box. So this classification can be done by softmax, because you know that in multi-class classification, we usually use softmax. But in the original RCNN, they did not use softmax. What was more popular at that time was SVM, support vector machine. Now here, to draw the bounding box, BB for bounding box, okay? To draw the bounding box, you perform something called as regression, where you start with a random bounding box and then you try to move it in such a way that it is closer and closer and closer to ground truth. Now, let us take a step back, because before we go into anything further, I have a few questions to ask. Firstly, please tell me this. Support vector machine is nothing but you have a bunch of data points like this. Okay, you have a bunch of data points and you try to identify a line that best separates these two classes. Now, in SVM, you usually are doing binary classification. But here, there is no guarantee that you are only looking at a binary class. You could be looking at 5 classes, because maybe there are 5 different vehicles that you are looking at. Maybe there are 100 classes. So how exactly are we using support vector machine here to detect car or truck or whatever it is, to detect that object from the sub region? Why exactly, or how exactly does SVM work in this case? Can anyone comment anything on this? So my question is, SVM is used for binary classification usually, but here there is no guarantee that we are performing binary classification. It could be multi-class classification. So how exactly is SVM used? We know that softmax can be used for multi-class classification. So if we were using softmax, of course, no problem. But how exactly does SVM work here? So what is being done here is, in SVM, you train, if you have 20 classes, you train 20 different SVMs. So for example, let's say you had third class, another class here, okay? This is another class. So now you have to perform something sort of like a, I would say, 3-class classification. Then all you need to do is you train one SVM like this, another SVM like this. So the purpose of, or rather something like this. So one SVM could be something like this line. Another SVM could be something like this line. Now consider these two SVMs, okay? 1 and 2. The first support vector machine, what can it say? Anything to the right of that. And now I'm also going to call, let me just denote this by a different color so that you are not getting confused. So this can be, okay, so now this is class 1. Everything in this blue dot is class 1. Everything in this green dots are class 3. And these red dots are class 2. Now you have 2 SVMs here. The first SVM can say if something is class 1 or not. It cannot distinguish between class 3 and class 2, but this first SVM, this line, can say anything to the right of that belongs to class 1. If not, it's not class 1. So it's like in the Silicon Valley, hot dog versus no hot dog, something like that. So this can say class 1 versus not class 1. Similarly, this SVM, this guy can say, SVM2 can say whether something is class 2 or not, because anything to the left of that is class 2. Everything else is the rest of the classes. And similarly, if we had one more SVM like this, let's say this is SVM number 3, then this SVM can distinguish anything that is class 3 or rest of the classes. So this is how you can use SVM for multi-class classification, where depending on the number of classes, you have that many SVMs. So here, if you were having 20 different objects that you are interested in, you will be training 20 different SVMs. Similarly, the regression part also, which detects the bounding box, that also needs 20 different regressions. If you have 20 classes, one regression will be good at drawing bounding boxes around cats. Another regression would be good at drawing bounding boxes around trucks. Another for car, like that, depending on how many objects that you are training your RCNN for. But here is another question. What is the ground truth for your regression and what is the ground truth for your support vector machine? Because you know the original ground truth. The original ground truth was whatever your image was, right? So if this was your image, you have a car image. Let me just copy that here. The car is here. The only ground truth which you are providing usually is something that looks like this. You have an image, you have a bounding box. So you will tell the algorithm, you will tell the neural network while training that the true class of whatever is there in this bounding box is a car. And the bounding box coordinates are x coordinate, y coordinate, width and height of the, so x and y coordinate are for this part, this kind of like origin. The width and height are the width and height of the, so this is the ground truth, the true class and the true location of your bounding box. So this information you are providing to the RCNN. But my question is not that. You know that SVM and regression are being applied not for the entire image. It is applied separately for each regions from the region proposal. And you have to do this for all the 2000 regions that are proposed. So what is the ground truth for this SVM? And what is the ground truth for the regression? Any thoughts? Like if the SVM has to be trained, how does the SVM know what is the reality? Because you are looking only at a part of an image. How do you know if this part of the image is car or if this part of the image is truck or something else? So to identify the ground truth, what you do is the following. So let's say your proposed region is something that looks like this. Okay, let me draw a rectangle. Let's say this was one of the proposed region. You look at a concept called as IOU, intersection over union. So you look at the total area combined by these two rectangles. So area, it's not direct sum of the rectangle, but the total area that is spanned by these two rectangles. So that is the union area. And intersection area is whatever is the area of this region. So that is the intersection area. So whatever is the intersection area divided by whatever is the union area, that is called IOU, intersection over union. So now imagine if IOU equal to 1, it means your proposed rectangle looks basically like this. If your proposed rectangle was, now I have a question, right? So let's say this is your proposed rectangle. Now just tell me two cases, okay? In case 1, the proposed rectangle is here. In case 2, the proposed rectangle is here. So case 1 is this guy, case 2 is this guy. In which case is IOU higher and why? So this is the proposed rectangle 1 in case 1. And this is case 2. Just give me logically, why is case 2 better? Because in case 2, the intersection area is higher. That is the first thing. And the union area is lower, because union area, that proposed rectangle is not increasing the union area. So the IOU in case 2 will be higher. So in case 2, there is a, so what you do is to propose the ground truth. So now I have to before processing the, these sub-regions, I have to let the algorithm know what is the ground truth for the sub-region, meaning I have to let my SVM know what is the ground truth for this case 1. I have to let my algorithm know what is the ground truth for the case 2. Now, let's say for case 1, the IOU equal to some number 0.23, right? Because it will be a number less than 1. Now, let's say in case 2, the IOU is 0.44. Then what I can do is, and one more thing I can do is, I can look at the IOU, and if IOU is greater than a certain threshold, then I can say that particular region, the ground truth corresponding to that particular region is whatever is the ground truth corresponding to this particular rectangle. So what is the ground truth of this original rectangle? It is car. Then I will say, if my IOU threshold is, let's say 0.3, then for this guy, I will classify it as background because it has neither truck nor car in it. But for this guy, because the IOU is 0.44, I will classify this as whatever is the ground truth of my original big rectangle. So here, the original big rectangle is enclosing a car. So the ground truth for this case 2 sub-region, which is this rectangle, is car. So this is how we can construct the ground truth for these sub-regions. And using that ground truth data only, we'll be able to train the SVM, because without the ground truth, how else will we train? Now, similarly, we can also train the regressor, where you know that, if you have a rectangle, something like this, if you have a region that looks like this, you know that you have this much overlap with the original ground truth rectangle, and using that you can say that the bounding box ground truth is something like this, and the original class, if IOU is, let's say, greater than 0.4, I will say for this sub-region the class is car, otherwise it is background. If there was a truck, I will say if IOU is greater than 0.5, it is like a truck, and otherwise it's a background. Now, if it is a car, I also need to tell where is the bounding rectangle coming. In this case, the bounding rectangle, we can say it's coming here. And this also we will pass as the information to this regressor. And regressor will try to initially make random predictions about the bounding rectangle, but it knows the ground truth. So it will try to move closer and closer and closer to the ground truth. Similarly, SVM will also make predictions. Initially, the predictions will be random. Initially, SVM might say, oh, this proposed region encloses background while it is actually showing a car. But then it will have a loss function, and the loss function will ensure that the SVM is also trained. So I will show you the entire network once so that you are clear. So just starting from the beginning, you have an input image which you convert to square shape, and then you get the region proposals. There are 2000 regions instead of 635 million regions. Each of the 2000 regions, you pass through a CNN. I mean, you pass through a convolution and flatten operation to convert it into a different representation. And then that representation is used for classification as well as for bounding rectangle drawing. How is the classification done? A multi-class classification is done using a multi-SVM framework. Bounding box drawing is done using regression. Now, what is the total loss of this neural network? Because even if you are correctly labeling what is there inside the bounding, inside the small sub-region, the bounding rectangle drawing may be wrong. So there is a mean squared error loss corresponding to how well the bounding rectangle is drawn. There is a cross entropy loss, which is associated with the multi-class classification. And you can simply add these two losses to get the total loss of your entire regional CNN. And this loss is what you are trying to minimize while training the RCNN. Now, this is a huge, we will implement this RCNN today in code, but you might have identified how complex this is, because you have to do this process for every individual sub-region in those 2000 regions for every image. Now, if you are planning to train an RCNN on a set of, let's say, 1000 images, every single image will produce 2000 sub-regions, which means 2000 multiplied by all the steps starting from here till end. You are doing it for 2000 multiplied by 1000. What is that? 2 million, right? For 2 million kind of collections of pixels, basically 2 million sub images. So it's like a very, very time consuming approach, but it was working when it was proposed. So if I'm not wrong, I think this was proposed back in 2014 or something. But this was one logical step ahead of, like the, I would say, dumb approach of looking at all possible rectangles and seeing whether inside that rectangle there is your object or not. So, but this was not too far away. It was not very, very smart. The only smart thing that we were doing here was, instead of looking at all possible combinations of rectangles, you are only looking at some possible combinations of 2000 rectangles. Now, we can implement RCNN, but I want to give you okay, there is a question, object proposal, how is it doing? So object proposal is done using an algorithm called selective search. So that algorithm does not involve any deep learning. It's like a handcrafted algorithm. So there is no learning involved. It's like a fixed, rigid algorithm. And this algorithm based on the pixel color, texture of a group of pixels, and the size of that particular geometry, based on these factors, you can propose potential regions where you might find your object of interest. So that is how the proposals are created. Now, before we implement the RCNN, let's do one thing. Let's also look at another algorithm called Fast RCNN. So tell me this much. In this entire RCNN architecture, let's look at this, right? In the RCNN architecture, what do you think is the most, I would say, most painful or most ineffective part? In your mind or in your opinion, what could be better in RCNN? Yes, SVMs, there are so many SVMs, so that part is a bit inefficient, of course. That's a good answer. Right. Region proposal is an issue. There is an answer about training on huge images. So the image size, we don't have too much control over. Of course, we can always downsample the image size, but assuming that we don't have too much control over what the actual input images are. The images are what it is. But other than that, region proposal is a problem, right? Because for every single image, you are looking at 2000 forward passes through the entire architecture. Similarly, in SVM, if you have 20 classes, you are training 20 SVMs. It's also not good. So in Fast RCNN, these two exact things were addressed. So firstly, just look at this. What are we doing in this particular region? In this region, what are we doing in this part? The only thing that we accomplish here is we are representing an input image in some format, right? The input image, which is 224 by 224 by 3, it is getting represented in another 4096 by 1 using a pre-trained neural network. So this could be a pre-trained neural network that has been trained on maybe millions of images from ImageNet. So essentially, you are trying to extract features from each of these region proposals, and you are trying to represent those features in another dimensional space. So here it is, the space has 4096 values. But why should you do this again and again and again for every single regions? You might as well just do this once, so that you are representing the entire image using the CNN, whatever the CNN knows, because CNN is pre-trained on millions of data set from internet. So you can use a pre-trained network, and you can already convert the features in your entire image, not just in your sub-region, features in your entire image, you could convert into a higher dimensional representation using a pre-trained neural network. And then you do your rest of the work. Then you somehow extract the interested regions and somehow you perform the classification and regression. But you don't have to be doing this part again and again and again. It's very inefficient to do this 2000 times, because here you have to do it for every 2000 regions. But people realize that this part can be moved to this place, kind of. Not exactly, but I'll show you. But this part you could move to a place where you are proposing the 2000 regions after you convert your image into some higher dimensional representation using a pre-trained CNN. So I have created an image which kind of shows you the difference between CNN and RCNN. So just look at this image for now. So in RCNN, you have input image. You find 2000 regions using the selective search algorithm. From 2000 regions, which you kind of resize into a square shaped image, you pass that through some pre-trained neural network like AlexNet to get what? To get your feature vector, which is 4096 dimensional vector. Then use that feature vector to do two things. One is classification to predict the class. Another is regression to predict the bounding box. So this prediction of class and prediction of bounding box is something that everything does. So there is RCNN, there is fast RCNN, there is faster RCNN, and last is mask RCNN. In today's lecture, we'll be discussing RCNN, fast RCNN, and faster RCNN. Mask RCNN we'll discuss in the next lecture. Now, what is the difference between RCNN and fast RCNN? In fast RCNN, this part remains the same. Just look at this. This part remains almost the same, not exactly the same. If you look at this part, you basically have a feature vector. Then you are performing classification on one side, bounding box regression on another side. Here also the same thing is happening. But please note this. Here they switched to softmax classifier. Here they were using SVM classifier. So this is one good thing that fast RCNN did. And if you look at faster RCNN and mask RCNN, which came later, they all use softmax. So only RCNN was using SVM. The second thing is, in fast RCNN, the way in which you get the 2000 proposed regions is very different. So you don't directly use selective search and you make a proposition for these are the 2000 regions, then pass through the AlexNet. You don't do that. What you rather do is you pass the input image through a convolutional neural network to get something called as feature map. Just one second. So once you get the feature map, which may look something like this, excuse me. So yeah, so this feature map is like a higher order representation of your image. It may not look like exactly your image. It won't be 2 dimensions. It can be multiple dimensions. It will be like a tensor. But this feature map will consist of, it will highlight the regions that are of your interest. Why? Because the CNN, which converts your image into this kind of like a feature map, already knows what are the relevant features for classification. So the CNN, the convolution operations, which are part of this pre-trained CNN, though the weights, I mean, the values inside that convolutional filter are attuned to recognizing or extracting the relevant features which are there in the image, which are useful for classification. Now, from this feature map, if you could, let's say you have 2000 proposed regions, right? Now from this feature map I have drawn here in X and Y dimensions, but this could have multiple dimensions because this feature map ultimately is a tensor. Now let's say you could say that, oh, this is the sub-region in the tensor, which corresponds to, let's say, this selective search rectangle. Just a second. Then basically what you're doing is you have a region proposal, something like that, that looks like this, and you are just trying to map it to the corresponding region in this feature map. There is no CNN operation involved in this mapping. The only CNN operation that is involved is in creating this feature map for the entire image. So instead of passing every single 2000 subregions through a CNN to create like a feature map, you create a feature map using the CNN for the entire image once. So you don't do it 2000 times, you do it once. And then for whatever regions that this selective search is proposing among the 2000 regions, you pick one by one, and then you map it to this feature map to say, okay, this region in the feature map corresponds to this subregion. So there is no way of bypassing the 2000 region thing, unfortunately, because the basic way in which this algorithm works is you have proposed regions and you try to identify which among the proposed regions are the best candidate. Where are the objects of interest and where are the bounding rectangles? So that you cannot bypass, unfortunately, but you can make the process faster. So see here, in this image, this CNN AlexNet will go through 2000 region proposals. But this VGG here will only go through forward pass through it once because, excuse me, because you are only passing the entire image through it once. Now, this is how fast RCNN works. Now let's do one thing. Let's implement the RCNN first in code. We will spend a bit more time in fast RCNN and faster RCNN, and then we can come back to coding the faster RCNN. So today we'll be actually implementing the code in Google Colab, not in VS Code. The reason for that is we will need GPU access if you want to run the code fast. So I have GPU access here. Even if you don't have the GPU access, it is totally fine. But getting a GPU access in Google Colab is fairly easy. So let's do one thing. First thing is I want to share the data with you, the file that I'm using. So this is my data set. And I will share this link. Okay, so this is the dataset link in the chat. So first do one thing. Please open this particular Google Drive link and make a copy into your Google Drive. And then I'll tell you exactly what to do. This code link also I will share with you. So this is the link to the Google Colab notebook. So please make a duplicate of this Google Colab notebook so that you can also run the code along with me. And this time, unfortunately, we will not be coding this from scratch because if we do that, it will take us at least 4 or 5 hours. But we'll rather go through the main parts of the code. Now, I hope you have access to both. So what you should do is the Google Drive RCNN data, you should make a duplicate in your Google Drive so that it's accessible to you. And Google Colab also, please, take a copy of that. Now you will have to install 2 libraries, which I have already done for myself. So you will have to install these 2 for yourself. Okay. Pip install Selective Search and pip install Torch snippets. So most of you will not have either of these. So this is the only thing that you have to install. Then the second thing is the following. To get GPU access on Colab, what you can do is go to runtime, change runtime type, And here, by default, you will have only CPU and one of the TPU, T4 GPU and TPU. You won't have A100 GPU. So right now I'm using A100 GPU. That is because here at the bottom, there should be a link which appears for you, which says purchase additional GPU units, computational compute units. And I have purchased for, I think, $11, just one $11 purchase. So, but this is not mandatory, but I have seen that this code runs much faster with GPU. Then what we do is the other change that you have to make is once you run this piece of code, your Google Drive will be connected with your Google Colab. So when you run this block, it will prompt you to connect your Google Drive. Then you just click this, you log into your Google Drive, Google account, and just give permission to read. Just continue. And then your Google Drive and Google Drive will be connected to your Google Colab. Then what you have to do is, okay, I think I have to install torch snippets. The next thing is, once your installation is done, here the path, right? This path will depend on how the folder structure looks like for you. So to know what your path is, click this folder icon, click this Google Colab icon, so that, it should be enabled. This Google Drive icon should be enabled. Then click Drive to expand it. My Drive, click that to expand it. And here, when you expand, you should see that RCNN data folder. Just click to expand it. And now here I have two things. One is this images folder and one is this data frame CSV file. So click these three dots, copy path, and paste that path over here for the path of this image root. And the df.csv also, you click and copy path and paste it just here. So maybe it won't change you as long as your, the place where your RCNN data folder is coming is also in your drive. Then maybe this is not needed, but otherwise it will be needed. So please check this. And another thing is, sometimes when you paste your things in your Google Drive, it appears in shared with me. So if I share something with you, it appears in share with me. But if it is in your shared with me, from there, you have to right click and create a shortcut. So you just right click and click add shortcut and add a shortcut to your My Drive. So then I think you should be good to go. Then what we can do is we can run the code. But basically before that, can I just ask you, how far along are you? Are you able to run part of the code? Are these blocks functional? Can you just let me know? Okay, awesome. Are you using CPU or do you have GPU access? But even if you have only CPU, I can show you the results and you can continue running your code. One more thing which may be useful to you, when you run your code on Google Colab, what happens is, okay, run pod is fine. But otherwise, if you are running on Google Colab, what happens is sometimes if your screen kind of sleeps, then the Colab running will get interrupted. So what I have done as like a shortcut is screen sleep prevention. Actually, there is this, what is it called? This guy, keep awake. Yeah. So go to keep awake Google Chrome extension. So you just install. So what I do is, if I'm running a collab, I just press this so that the screen will be awake. And then I won't run into the risk of, my collab disconnecting because my screen has slept. Okay, so basically the first part is just displaying the content of the CSV file, which you can open and see what is there. Basically, it is bunch of images and then the annotations of those images in the CSV file. So that the ground truth rectangles, you will not draw directly on top of the image in the data because then the data will be manipulated, right? Manipulated meaning you have a dirty data. Instead, the way the data looks like is something like this. So here the training data has, this is different data set, but I'm just showing you, see these images. There is no annotation in the image, but annotation come here in this file for that particular image. These are the annotations. For example, height is, for bounding rectangles, for example, yeah, see, bounding box, B box, 250, 616, 43, 124. So those are the X coordinate and Y coordinate of the starting origin. And then the other two ones are the width and height. So this is usually how training data will look like for object detection. So just run that also. And then the rest of the code, what it is doing is basically implement different parts of the RCNN. So in one, and some custom classes are also defined. So actually this code I did not write from scratch. I had to take significant help from cloud, Anthropic cloud. But what I have realized is that getting a proper working code in RCNN is not very easy because there are many parts that are at the same time functioning. So, but now I'm happy that I have this working code. So just let me just show you what the code is doing. So first it is reading the data set from the root. So image root and reading and displaying. So you see, this is how the ground truth data image on top of which the annotated rectangle are added will look like. So here I think it's like a two-class classification, truck or bus. So bus class you can see here. It's feeble. You can barely read it, but you see the bounding rectangle and the bus. This is a very bad quality image, but this is how the annotation is. And here actually the car is being annotated as, maybe rest of the things are being called as truck. I don't know what is the definition of a truck, or maybe something that has a carrier behind is called as a truck or mini truck or whatever, but all of them are annotated as truck. Now, what we do is, so first here we have this extract candidate function, which is where the selective search runs. So selective search, we installed a library. If you remember, pip install selective search. So we are not bothered about internally what happens in selective search, but basically selective search algorithm will give us the potential candidates for those 2000 regions. So that is defined in this function, the whole thing. And here we are skipping, here we are eliminating few regions. So if selective search proposes duplicate regions, we will eliminate the duplicate. If the selective search regions are too small, we will eliminate it. If they are too large, we will eliminate it. And only those regions which do not fall into this category are being selected. Now, I will show you how a selective search region will look like. But once we have the selective search region, what is the next thing to do? We need to know what is the ground truth for the selective search region. Ground truth meaning whether the region includes a truck or a bus or nothing, and where is the bounding rectangle. So we first need to know the IOU, right? So we need to know the intersection over area for that particular region from the selective search compared to the ground truth rectangle. What is the ground truth rectangle? If this was the image, this will be the ground truth rectangle. If this was the image, these will be the ground truth rectangles, these three green rectangles. So for the selective search region, we assign the ground truth value depending on the IOU. So that is why we have this extract IOU function. I don't have to explain it line by line because then we will never end this lecture, but I'll at least show you what exactly each of them are doing. Then, so see here, candidates equal to extract candidates from image. So this is the input image IM. Extract candidates is the function which runs the selective search. Then from the candidates, now you can see that these are the bounding boxes from the candidates, the selective search regions, candidate regions in the whole image. So this IM at the top is simply the image name. We are just calling it as IM. But you can see that inside these region proposals are, by the way, covering most of the image. And now all we need to look at is which proposed region contain our actual object of interest. And object of interest here, you can see that there is something like a bus or something here. So maybe this rectangle will be finally what is picked, but we will get there. Then what we do is, for each candidate, we extract the IOU. Where is the extract IOU function? Extract IOU function is being called here, but it is defined up here. This is the extract IOU function. So for every candidate rectangle, we extract the intersection over area. If it is greater than a certain threshold, we say it belongs to that particular class of the ground truth rectangle. Otherwise, we ignore it. And then, yeah, this part is also basically for ground truth bounding box. But I just want to show you. So yeah, so in the example image that I'm displaying here, the IOU for the best candidate is turning out to be only 0.14, meaning there is not significant overlap between the best possible proposed region and the actual ground truth. The IOU is only 0.15, 0.145. The best possible value for this is 1. But now what we do is, this is the part of the code which takes a bit of time to run. So let this first finish running. So here you can see that the actual ground truth is here. The ground truth is here, but best candidate bounding box is this. So now intersection area is this itself. Union area is this. And this is turning out to be 15%, close to 15% of the total union area. So this was the 0.145. Now, can you let me know in the chat if you are able to run up till here, or whether you are facing an issue in running the code? Just let me know. And since I have already run the remaining part of the code, I will just show you some part of the results. So finally, I selected a random image while testing. So here, what we are using is, okay, in progress, right? Are you using CPU or just you have access to GPU? Anybody running this in, okay, T4 GPU, that will be better. Okay, anyone? Okay, A100 GPU will be good to have. Because in this course, anyway, we'll be training some models from scratch. So at least for this month, if you just purchase the GPU, I would say it's totally worth it. But while the code is running, let me just show you finally in the testing what I have achieved. So, okay, so I ran for 5 epochs and my best validation accuracy is like close to 80%. Training accuracy is 97%. So this is how it looks like. So, and can anyone tell me here? Okay, don't tell me the accuracy, at least tell me the loss. What does the loss mean here? Does it mean that my bounding boxes are identifying the object inside it really well? Or does it mean that my bounding box is being drawn in a very nice way, that the bounding rectangle is drawn at the right portions? Or does it mean both? Does it mean that my bounding box is being drawn at a certain place very well, and also inside that bounding box, whatever it is being classified very well? What does the loss mean here? Is it the classification, or is it the bounding box regression, or is it a combination? Right. So basically it's a combination. We are not just trying to do classification. We are not just trying to find the right place of the bounding box. We are trying to do both. We want to know what exists inside the bounding box. We also want to know the right position for the bounding box. So the loss, as I showed you here, is a combination of the cross entropy loss and the mean squared error loss. Over here, I had shown you see, so we have the cross entropy loss for the classification of the object inside the bounding box. We also had the mean squared error for saying how good your bounding box drawing is, right? So you are adding those two to get your combined loss. So the plot that you see here is for the combined loss. And as somebody mentioned, the validation loss is not reducing too much. So which is a sign of maybe overfitting, but not yet. But here you can see that when you plot the accuracy, after some point, after like 3 epochs, your training accuracy is continuing to increase, but validation accuracy has started to decrease slightly. I mean, these are only few iterations. It's not there. It's not good enough to make a comment. But if I were to make a comment, I would say, yeah, kind of maybe overfitting is happening. So we might as well be better off stopping the training at 4th epoch or something. But training accuracy is good, 95, 97%. Validation accuracy is decent, like 80%. But these are my results. Now in testing, I selected a random image, which happened to be like a toy. And here you can see that the final proposed region is this. This is the proposed bounding box. And you can see the class here. The class of that bounding box is truck. So truck is correct. The even better bounding box would have been something that is just enclosing this, but maybe in the region proposal that did not come up for this particular image. So, but for practical purposes, we have got the thing correct, but you can see that half of the image is being consumed by this bounding box. And in testing, we can, if any one of you have managed, all you need to do to play with the test data is change this number, change the index of the test data set of 1, of 5, or of 10. Then you can change this image randomly and you can see whether, you are getting a good bounding box or not. But let me also check how much my code has progressed. Okay, so my previous thing has finished running. So I just need to run the rest of the code just to show you. Okay. Yeah, so this is the 3-class classification that I mentioned earlier. So here the class 0 is bus, class 1 is background, and class 2 is truck. Ideally, it's a 2-class classification. Actually, you know what? Sometimes here it could be multiple classes also, because a bus and a truck can be in one image, right? That is also possible. In usual classification, you will have only either or, but here it could be both. So we can't strictly call this as an original 2-class classification problem. But in any case, I'll show you how the training looks like. So here we are downloading the pre-trained VGG16. So VGG16 is a famous model. It was, if I'm not wrong, it was released in 2014. It came second in the ImageNet competition. So it was one of the famous models. AlexNet was the winner in ImageNet competition in 2012. VGG16 came to second. Are we to specify how many classes we need? Yes. So we have to specify the classes because the algorithm has no idea whether we are looking at buses, trucks, and background, because in many images there are many other objects, but we are specifying, right? Because in our training data, the bounding boxes are there available only around buses or trucks. So we have to also say that we are only looking at those two things plus the background. Then I downloaded the pre-trained VGG. Then this is the class for the RCNN. Yeah. So here is in this train batch function definition is where we are actually performing the training. This validation batch here is where we are actually performing validation. And when you run this part of the code, this part of the code, you will see the accuracy displayed as a function of epoch. So here you can see that. So my numbers are changing this fast, like 76 out of 400. If you do the same thing with GPU, by this time, only 1 or 2 batches would have been finished processing instead of 400. So that is how fast the A100 GPU is. And like this, it will run for 5 epochs. Okay. So this is the RCNN code. Now, today, I also want to discuss with you about one more model. So fast RCNN and faster RCNN, let's spend some more time and let's implement that in code. But before that, let us also know the historical significance of this paper. Nobody is using RCNN in today's lecture. But then why am I teaching you about RCNN, right? The reason why I'm teaching you RCNN is I could dump YOLO in front of you right now, YOLO V8 or YOLO V11. But then what is the significance of these models if we don't know the struggle that we as humanity took to reach this stage? So RCNN has a historical significance in being one of the first models that showed that object detection from images, multi-object detection from images are actually possible using deep neural networks. So that was the significance of RCNN. Then in 2015, Fast RCNN was introduced, but immediately after that, Faster RCNN was also introduced. So now if you go to Fast RCNN GitHub repo, you will see something interesting. So they have said that this has deprecated, meaning this is not under use anymore. Nobody uses Fast RCNN also. People have moved on beyond Fast RCNN. I will tell you what exactly is Fast RCNN and what exactly is Faster RCNN, but I just want to give you a historical context. These papers have anywhere between 45,000 to 50,000 citations. So RCNN has 44,000. Fast RCNN has something similar. This one has 55,000. Mask RCNN has 44,000. So these are highly cited papers in the computer vision literature. But I would say most of the modern, I would say, object detection techniques are a variant of Faster RCNN. It's not a variant of RCNN. It's not a variant of Fast RCNN. Then Mask RCNN is used for image segmentation, which we will discuss in detail in the next lecture. But now let's come back and focus on Fast RCNN and Faster RCNN. So I have prepared this image just for to let us do that. So as I discussed before, the main innovation in Fast RCNN were two things. I mean, softmax was not an innovation. It was just a change. And anyway, softmax is a better thing to perform multi-class classification than SVM. So this was the number one thing, which somebody mentioned in the comment that one inefficient part of the RCNN was having multiple SVMs to perform multi-class classification. So that was fixed by having a softmax. The second thing that Fast RCNN do, which actually made things fast, was preventing the main, pre-trained neural CNN to be performing forward pass again and again and again 2000 times. So RCNN was doing that, but Fast RCNN stopped doing that. It made only one forward pass of the entire image, not the individual regions. The entire image was made to forward pass through the pre-trained CNN like VGG16 to create a feature map. Now this feature map is what? Feature map is a higher dimensional representation of the features that are useful in the image. Now from this feature map, you can identify parts of that tensor. So this feature map will look like some tensor. So a subsection of that tensor may correspond to some selective search proposals. So selective search proposals are still being done here. The difference being proposing the 2000 regions in selective search proposal is not a difficult thing. Proposing those 2000 regions are fine, but passing those 2000 regions through CNN is the worst thing to do. So that we are avoiding. So we are still generating proposals of 2000 regions, but then instead of using a CNN to convert that into a feature vector, here those selective search proposal regions in two-dimensional image is converted into a higher dimensional region inside the feature map by performing a mapping. So if you have a tensor, which let's say using 2D, I am representing like this, although this may be multi-dimensional, then I might be able to say that, oh, this region in my feature tensor might correspond to this this proposed region. So you are bypassing now the pain of having to pass these 2000 proposals through CNN, and then you perform the rest of the things. So this is what Fast RCNN was doing. Now, again, you might notice there is a pain here. Selective proposal is not a deep learning algorithm. It's like a handcrafted algorithm. There is no change to that algorithm. So why should we look at 2000 regions? Why not 100? Why not 10? Why not 300? Anything is possible, right? And to propose these 2000 regions, why are we using a handcrafted algorithm? Why can't we use a neural network? So that was the idea behind Faster RCNN, where they entirely got rid of this selective search proposal handcrafted algorithm. Instead, they replaced it with something called as RPN, which is like a region proposal network. It's a neural network which will propose some regions. Propose some regions from where? Propose from some regions from the shared feature map. What is this shared feature map? shared feature map is something that looks like this. The image converted into its features using a pre-trained CNN. So from this, to find the selective proposed regions, you don't look at the image again. You pass this whole thing through a region proposal network, and then you find that, oh, some sub-regions actually can be corresponding to a car, or it can be corresponding to a truck, or it can be corresponding to a background, something like that. So just look at the common things, okay? So this part is again common. You have a higher dimensional representation of the input, which you are converting, you are performing a classification on. You're also performing a regression, the bounding box regression and softmax classifier. So these two things are standard in Faster RCNN. The input image being passed through a CNN backbone, it could be ResNet, it could be VGG, it could be LXNet, doesn't matter what we are using. So this is also common. So if you look at the Fast RCNN, you have a convolutional neural network backbone to create a feature map. Here also, you have a convolutional neural network backbone to create a feature map. But in Fast RCNN, so this is Fast RCNN, you were using selective search to propose the 2000 regions, but here you use a region proposal network to get some proposed regions in the feature map, not in the image, in the feature map. And how many such regions? Only like, let's say 300 regions. So now you have a much better and much smaller set of regions to look at instead of 2000 samples. So you now have a much better representation of the features in the image because you have a CNN backbone, this guy, and you have a much better selection of your subset of regions where you might find your object of interest. You have 300 of them. And the good thing is this region proposal network is a learnable network. That neural network can be trained again and again and again through back propagation to make it much better. Here, the selective search algorithm, you don't make it better. It's already there. It's fixed. There is no back propagation to make this algorithm better. So that way, you now get rid of the rigidity of your selective search proposal algorithm. So this was the second innovation that people immediately figured out you could implement in Faster RCNN. So the names are similar, but the idea is also very similar. And although the paper year in Faster RCNN shows 2016 and this one shows 2015, my knowledge is that this Faster RCNN was in fact proposed few months after Fast RCNN, when people immediately recognize that, oh, now that we have a CNN backbone, we don't even need the selective proposal. We can simply have another neural network to find that. So this was Faster RCNN. And let's do one thing. Before we move on to Mask RCNN in the next lecture, today let's implement Faster RCNN. And here I will show you one thing which you will find tremendously useful. So firstly, about dataset. Which dataset are we going to use? We are going to use like an aquatic animal dataset. So aquarium dataset from RoboFlow. So just type this and this will open your RoboFlow. It should ideally show this link. Then open that. RoboFlow anyway, we'll be spending a lot of time on in the last part of this course, but I need aquarium dataset, RoboFlow object detection. And here, just go to where is the dataset link? Yeah, so this is the link. So just go to this link. Yes, I will upload the file link in the dashboard. I will also share this Fast RCNN code in the chat right now. So just, this is the Google Colab notebook. So just make a copy of that. But to get the data set, go to this link, this public.roboflow.com. This link I just pasted in the chat. Then go to this Coco JSON. So Coco I just mentioned in the last class. So Coco dataset was the benchmark data set for object detection, image segmentation tasks. So common objects in context. So there was like a COCO competition going on, just like ImageNet competition for classification. So here, click on COCO JSON and you might be prompted to log in. If yes, then just log in. And then here, click download zip to computer. So this file is not very big. I think it's only 76 megabytes or something. Yeah, 68 megabytes. So just download that. And once you download it, this is how the dataset will look like. Once you unzip the file, this is how the dataset will look like. So it will have a train, test and validation folder. Okay. Now in train folder, if you open, usually what do you see in a classification task? You may see two subfolders. If there are two categories or six categories, you will see six subfolders. But here you don't see any subfolder. You simply see bunch of images, but you also see like a JSON file. So the subfolders are basic. I mean, these images are basically bunch of aquatic animals from various aquariums. And there are, I think, 6 or 7 categories of these aquatic animals. And this JSON file is very interesting. Can anyone confirm if you can see the JSON file in my screen sharing? I'm just want to make sure this coco.json. Okay, thank you. So in this JSON file, just check this. There are 8 categories. I mean, fish, then I think ID 0 is none. I guess that is background. So fish, jellyfish, penguin, puffin, shark, starfish, and stingray. So those are the categories. And then every images have an ID and file name. So this file name, right? This image 249 JPEG.jpg, then some big thing.jpg. So those are the names of the images in these files. And then if you scroll down a little bit in this JSON, you will see that every image has an ID and every ID has a category ID. Category ID is the class, and they have a bbox, not ID, like a bbox 4 numbers associated with this, which is the bounding box width, height, and the starting point. And you have the area, then that's it basically. So this is the standard way in which the JSON-based notation for the COCO dataset looks like. So that's the reason why we downloaded it, because many models directly accept this kind of a data. So what I have done is I have uploaded this COCO dataset onto my Google Drive. So let's see if I can find actually I can just share the dataset itself. I'll find it. Anyways, so let me just first install these two, pip install selective search and pip, yeah, only selective search is needed. So this I'll install. And here also I am using A100 GPU. I don't want to use any other GPU. And connect to Google Drive. Can anyone mention in the chat if you managed to download the COCO dataset from RoboFlow? So all you need to do is this: download it, unzip it, upload it to your Google Drive, and use that drive link. That's all you need to do. So that link you can just paste here in this part of the code. That's it. Okay, so once you connect your Google Drive, just okay, so that is loaded, and all you need to do is upload, and you should have this path ready, and then some transformations. And here is where rest of the things happen. So the architecture is fairly similar and straightforward compared to the previous one. Okay, data set is not defined. So Yeah, so these are my IDs of the data set: fish, jellyfish, penguin, puffin, shark, etc. And here we are just extracting those names and then loading the train data set. Then here is a sample data where draw bounding boxes. It's not defined. I guess. Yeah, matplotlib.pyplot will be needed for drawing. And so just let me know, guys, if you have managed to reach till here, or I think this might be part of the, yeah, it's not. Let me check. I don't think this needs any special function. Was used without being imported. Okay. Yeah, this was the import that was missing. All right. So now these are the bounding boxes, right? And the category I am not displaying here, but we could display it from the JSON file. Then there are 447 images in the training data. And here, I think we are using RESTnet, if I'm not wrong. Let me just go down and I'll confirm. Here we are using MobileNet, not RESTnet. Initially, I was playing with RESTnet a little bit. Then number of epochs is 10. Actually, this code is not that slow as the previous one. It's actually pretty fast. Okay, TQDM is not defined. Have you managed to run till certain point? Just let me know. Did you display this image yet? Because training might take a little bit of time, but did you manage to display a sample image from this, like this? Just let me know in the chat. Okay, got it. And while this is running, if my final image has not disappeared yet, I'll just show you what the output looks like. So basically the output will be similar to what we got from RCNN. There will be multiple bounding rectangles around multiple aquatic species, and it will also display the name of that species. So that is what we are looking at, right? So let me just make sure that. Yeah, so now we are able to run. So some in my code, some items were missing. So if you took a duplicate, just take duplicate once more now. So I was missing some imports, which is why the code was not working. So this TQDM was missing, and I was missing the pipe matplotlib import. So just make sure that you have those, you have the latest version of the copy from now. And the 10 iterations should not take any time. And at the end, I'll show you the result. But I think we are almost there. We are pretty much done with the main part of the lecture. The remaining matter is just to display the result. Now, mask RCNN, although we will cover in detail in the next lecture, I will just tell you what is the extra thing it does. If you look at mask RCNN, it's exactly same as faster RCNN. It has a RESTnet or VGG or mobile net, whatever is the background that is being used, right? Then the shared feature map is nothing but the higher dimensional feature map representing the features of interest. So this pre-trained neural network will convert the images into a higher dimensional representation. Then RPN, the region proposal network, will propose maybe 300 regions instead of 2000 regions. And those regions are now used for creating three things. One is a classification, another is a bounding box, and another is a segmentation. So this is the other main task, image segmentation, which we are in general interested in this bootcamp. So we are interested in object identification and image segmentation. And if you remember, we had implemented a image segmentation using YOLO V8 segmentation dot pre-trained. So this model we had used in the last lecture. So if the segmentation was not mentioned, we would have just gotten object detection. But when we mentioned segmentation, we got the contours of the people who are walking in the street. So just notice that that's what we'll be doing this time. So now this running has finished. Let me just check. Okay, so this is a random test data set. Okay, and here you can see the result. There is a shark here, shark, stingray, some random fish. I don't see the name. That's it. And if I change the number here, test data set 15 instead of 5, this should hopefully display another set of. So here you can see a starfish. This is a starfish. So this is the aquarium data set where you can play with. I mean, this is a toy data set. This is by no means an industrially useful data set, but this is like a toy data set which you can use to get familiarized with the actual object detection algorithm from scratch. So I think with that, we can wind up today's lecture. But what I want to ensure is that please message me after running the code if you have managed to get the result, or put it in the Discord if you haven't managed to run the code for some reason. The common issues that you may run into are mostly library importing issues. Other than that, the code I have spent huge time on to get it in a working shape. So I don't think you should ideally. Yeah, so updated code will be on the same link itself. You just need to make a copy once again. But anyways, I'll share the link once again. So this is the link for the Faster RCNN. So just to recap, there are 4 types of algorithms in similar category. First is the normal vanilla RCNN, then fast RCNN, faster RCNN, and mask RCNN. I forgot the year in which mask RCNN was introduced. Maybe it is 2017, if anyone can check. This was 2017, yeah. So mask RCNN was introduced later. So the timeline was, this is how it goes. Okay, and you can see that this one is smarter. So in RCNN, just to recap, you start with region proposals. You have 2000 regions. You pass each of the region through a pre-trained neural network like AlexNet or VGG. Then you extract features on a feature vector, and then use that feature vector to perform classification and perform bounding box regression. The classification was very bad. It was like a multi-class SVM, which later changed into softmax. Then for the rest of the models, they ended up using softmax only. Bounding box regression is common. It's used in all the models. Fast RCNN, what they did was they prevented you from passing the 2000 region proposals through the main neural network backbone. Instead, you move the backbone to before the proposal. So you use the backbone to extract features, then propose the regions, and you map the features. You map the proposed regions into the feature dimension, and then use that 2000 regions for performing classification or regression. But here also the problem was you are using selective search algorithm, which is not like a, it's not a smart algorithm. It's a hand engineered fixed algorithm. And Faster RCNN, what they did was they nicely eliminated this selective search and they introduced RPN, region proposal network, which is another neural network. So this neural network will learn to propose better and better regions. The CNN backbone is anyway pre-trained, so it is already good at extracting features from the image. Then at the end, you have the feature vectors or feature representation, using which you perform softmax classification or bounding box regression. The only difference now the mask RCNN brings, which we will discuss in detail, is how the masking, the segmentation works using a mask. So with that, let's wind up today's lecture. I hope you understand the object detection part of this huge area of research and huge area of industrial interest very well. Of course, better than CNN, RCNN, you have YOLO. We will not, in industrial settings, we probably will be using YOLO V8 or later models, but it is very good to know where we started from. Like, it's very good to know how bad the initial models were before we even appreciating or before we even coming to the details of YOLO. So thank you so much. We will meet again on Thursday, same time. Take care until then. I hope you enjoyed the lecture. We'll see in 3 days. Bye.